Hello, everybody. This is homework from chapter 6, and in it we will be doing problems 1, 7, 22, 24, 36, 45, 46, 52, and 62. Let's begin. Chapter 6, problem 1 states, let me get there. Chapter 6, problem 1 says, you push your physics book 1.5 meters along a horizontal table with a horizontal push of 2.4 newtons, while the opposing force of friction is 0.600 newtons. How much work does each of the following forces do on your book? Your 2.4 Newton push, the friction force, the normal force from the tabletop, and the gravity. What is the net work done on the book? Okay, so your 2.4 Newton push goes 1.5 meters. And so we have work equals F d cos theta. So 2.40 newtons. And that was 1.50 meters. 1.50 meters. Cos 0, which is 0, equals 3.60 joules. That's A. For B, the friction force is going to be in the opposite direction. So that's 0.600 newtons times 1.50 meters times cos 180, and that's going to give you a negative 0.900 joules. For the final two, you're going to get 0 and 0 because the forces act perpendicular to the direction of motion. So the first one is goes up, and that would be cos 90, and that's 0. So, and the second one goes down, and that's cos 70. So that's 0 as well. And finally, we're asked to determine the total work done on the book, which would be work net equals work of U minus work of friction, which is going to be, 3.60 joules minus 0.900 joules. That's going to give you a 2.70 joules. And that's chapter 6, number 1. Problem 7, chapter 6, states two blocks are connected by a very light string passing over a massless and frictionless pulley. So what happens is we've got something like this. Here's your pulley. You got this guy, he's 12 newtons. And he's pulling this guy. And that's 20 newtons. Here's your pulley, it's massless and frictionless. And so is the string. How much work is done on the 12 Newton block by gravity? Oh, wait, does it tell you how far? It goes 75 centimeters down. So if that goes 75 centimeters down, that's got to go 75 centimeters that way. It's the same string. How much work is done by gravity, the tension in the string on the 12 Newton block? So let's go ahead and do this. So 12 newtons, that's the force, times 0.75 meters, times cos 0 is going to give you 9 joules, 9.00 joules. And the tension on the string, so 12 newtons times 0.75 meters times cos 180 is going to give you negative 9.00 joules. All right, let's see. How much work is done on the 20 Newton block by gravity, the tension in the oh, is there friction there? Traveling at a constant speed, the 75 to the right. Frictionless pulley. How much work is done? Let's see. Okay, well, let's just keep on going here. Okay, so how much work is done on the 20 Newton block by gravity, the tension in the string, friction, and the normal force? Let me stop and read this problem for a second. Okay, part B. Let's see. How much work is done on the 20 Newton block by gravity? By gravity, this is 20 newtons times 0.75 meters times cos 90. So that's going to give you a whopping 0.90. And then by the tension in the string. So this is going to be 12 newtons. Wait. Newtons, that's right. 12 newtons, that's times 0.75 meters times cos 0. And that's going to give you, again, 9 joules. Let's see. Then, let's see. Gravity, tension, spring, friction. Is going to give you 12 newtons of force. Times 0.75 meters times cos 180. And that's going to give you negative 9 joules, negative 9.00 joules. And finally, the normal force. The normal force is going to give you an angle of 90 degrees, which is going to be 0. Theta equals 90, so the work is perpendicular, so that's going to be 0. All right, for C, the work total by each block, you've got work for negative 9.00 joules plus a 9.00 joules. So you're going to get a 0 for the work total, the net work, right? The net work. Obviously, we have work done on it, but when you add up all the work done on it, you're going to get 0. All right, chapter 6, problem 22 asks us to use the work energy theorem to solve each of these problems. And it says you can use Newton's law to check your answer. A skier moving at 5 meters per second, so 5 meters per second, encounters a long, rough, horizontal patch of snow having a coefficient of kinetic friction, so mu k is going to equal to 0.220 with her skis. How far does she travel on the patch before stopping? Okay, suppose the rough patch in part A was only 2.9 meters long. How far would the skier be moving when she reached the end of the patch? At the base of the frictionless icy hill that rises 25 degrees above the horizontal, a toboggan. Okay, so that's a different problem. Okay, so we are going to use the work energy theorem, which says the change in kinetic energy is going to be equal to the work done. So we have a delta 1/2 mv squared equals F dot D. Okay, so all right, so we have delta 1/2 mv squared equals, and it's a horizontal patch. So it's mg mu k times d. That F is the force of friction, which I have here, the normal force times the coefficient of kinetic friction. So we didn't need mass, and that's good because it wasn't a quantity that was given. So we're calculating for D, so we've got, we know she stops. So I'll do the 1/2 times 5 meters per second, that's quantity squared, divided by 9.8 meters per second squared, that's G, times mu K was, what was that? 0.22. 0.220 is going to give me D, and I'm going to go ahead and get that from the solutions. Let's see, what do they have here? I think I have different solutions. Well, let me just go ahead and calculate. Let's see. Long horizontal patch with her skis. How far does she try? Okay, so let's just calculate that. I don't like that calculator. 25. Oh, wait. Clear. 25 divided by 2 times 9.8 times 0.22. It's going to be 5.79 meters. 5.79 meters. That is A. Okay. Let's see. So suppose the rough patch was only 2.9 meters long. How fast would the skier be moving when she reached the end of the patch? All right. So let's see. Let me pause, clear my board, and do that. Okay, so how fast would she be going? So I set up the problem here, 1/2 mv final squared minus 1/2 mv initial squared equals mg mu k times d. So these m's are going to go. So let's see. We have d, right? Let's see. Yeah, we have, suppose the rough patch was only 2.9 meters long. So we have 1/2 times 5 meters per second quantity squared minus 1/2 times v. Oh, wait. No, sorry. This is not. That was, let me just get this. All right. 1/2 v final squared minus 1/2 times 5 meters per second quantity squared equals 9.8 meters per second squared times 0.22 times 2.9 meters, right? All right, so let me go ahead and determine this. On clear, 9.8 times 0.22 times 2.9 equals, that's going to be equals 6.2524, 6.25 joules, or wait, not joules, it's joules over kilograms, times 2, so I could take that out, and then divided by 25 meters per second, meter squared over second squared. So times 2 divided by 25, and then take that to the power of 0.5, and I get 0.7 meters per second. That's how fast she would be going. All right. Okay, Finally, we're given at the base of a frictionless icy hill that rises 25 degrees above the horizontal. A toboggan has a speed of 12 meters per second towards the hill. How high vertically above the base will it go before stopping? Okay, so we know delta mv squared. Oops, sorry. I don't know what I'm thinking there. Let me clear. No, just erase. All right. We're going to trade in that 1/2 mv squared for mgh, and it's frictionless, so I don't have to worry about that. Okay, so how high vertically above the base will it go before stopping? So that's cool. All right, so let's see. 1/2 mv squared equals mgh, so these guys go. All right, so how fast are we going there? We're going 12 meters per second, so 1/2 times 12 meters per second, quantity squared, divided by 9.8 meters per second squared is going to give me h, the vertical height. Let's do that. 12 squared equals, divided by 2 equals, divided by 9.8 equals 7.34 meters. So whatever that will be the vertical distance. Doesn't really matter. The 12 or whatever 25 degrees is irrelevant. It's still will go 7.34 meters regardless of what the angle of incline is. All right, we are on chapter 6, number 24, which reads, you throw a 3 Newton rock, vertically into the air from ground level. You observe that when it is 15 meters, 0.0 meters, above the ground, it is traveling at 25 meters per second upward. Use the work energy theorem to find the rock speed just after it left the ground and its maximum height. All right, so delta mv squared, delta 1/2, delta ek equals work. All right, so let's find the work. So 1/2 mv final squared minus 1/2 mv initial squared equals force times distance. So I got to know the mass of that rock. 3 newtons divided by 9.8 meters per second squared, which is clear. 3 divided by 9.8 equals. That's going to be the mass of the rock is 0.306 kilograms. So let's go with 0.31 kg. All right. 1/2 times 0.31 kg times V final squared minus V initial squared equals 3 newtons times 15 meters. Okay, let's just go ahead and, all right, 3 newtons times 15 meters. Let's go ahead and times it by 2 and divide by 0.31 kg. And go ahead and solve that on clear. 3 times 15 equals divided by 0.31 equals times 2 equals. I'm going to get V final squared minus V initial squared equals 290 meters squared over seconds squared. All right, let's see. So V initial squared was, no, V final squared is 25 meters per second. So this is V final is 25 meters per second. So we've got, I'm going to do this. I'm going to say 290 V final squared minus 290 meters squared over second squared equals V initial squared. And what was V final squared? So that would be 25. So 25 squared. 625. 620. 25. Oh, it's got to be plus that. Wait. This. I see what I did. I forgot to put this negative here. It's doing negative work. So in light of that, we're going to add this, and then we're going to get V initial squared. V initial squared. So yeah, don't make that mistake. Okay, so now we have, boy, this is so limiting having this little board here, but 625 meters per meter squared second squared plus 290 meters squared over second squared is going to give me V initial squared. So let me take the square root of that and get V initial. So plus 290 equals power of 0.5 equals, I get 30.24. So V initial equals 30.24 meters per second. All right. Part B. Number 36. All right, this is chapter 6, problem 36, which reads, a child applies a force parallel to the x-axis to a 10-kilogram sled moving on the frozen surface of a small pond. As the child controls the speed of the sled, the x component of the force she applies varies with the x coordinate of the sled as shown. Calculate the work done by the force when the sled moves from x equals 0 to x equals 8 meters, from x equals 8 meters to x equals 12 meters, from x equals 0 to x equals 12 meters. All right, so the work is going to be the area under the curve. It's something like this. 12, this is 12, this is 8 meters, and this is 0, and that's meters. This is S in meters, and this is force in newtons, and right here at the very peak we've got 10. So A, from 0 to 8, 0 to 8 meters, we've got just a triangle, right? 1/2 times length times width times 8 meters times 10 meters. That's going to be 40 joules. And then from B is 8 to 12. So we're going to have 1/2, and that's 4 meters times 10 meters. And that's going to be 20 joules. And then the entire thing is 40 plus 20 or 60 joules. Okay, that was problem 36, chapter 6. All right, chapter 6, number 46 is called half of a spring and reads, suppose you cut a massless ideal spring in half. If the full spring had a force constant of K, what is the force constant in each half in terms of K? So the force constant F equals Kx. So now if I have a force and I apply the same force, but I only get half of the displacement, my force constant is going to go up. So if I have K equals F over X, and I apply the same force, and I only get half, my force constant is going to go up twice. So half the spring makes it stiffer. You're going to have to apply, if you apply the same force, you only get half the displacement, so it's double. If you cut the spring into 3 equal segments instead, what force constant of each in terms of K? It's going to have to go up as, we're going to get 1/3, so it's going to go up as 3 times, right? So you make it smaller, you get half the displacement, and your force constant goes up. This is Hooke's law right here. Hooke's law says the force required to displace a spring from its equilibrium position is going to equal to that spring constant K times the amount of displacement from the equilibrium position. That's Hooke's law. All right, now we're going to do chapter 6, number 52. And it states, it is 5 kilometers from your home to the physics lab. So X equals 5 km. As part of your physical fitness program, you could run that distance at, so you have your choice of running at 10 kilometers per hour. Or you could walk at a leisurely 3 kilometers per hour. B is 3 km per hour. And now at 10 kilometers per hour, you got your power is 700 watts, which is 700 joules per second. At 3 kilometers per hour, your power expenditure is 290 watts or joules per second. So now I need to know which one is going to burn the most energy. So what I need to do now is find out how long it takes me to either run it or walk it, and then find out, do my conversions. So we've got 10 kilometers per hour. I'm going to multiply that by 1 hour over 3,600 seconds because I need to do that. So let's see. On clear 10 divided by 3,600. Going to be 0.0027 kilometers per second. Okay, times 5. Take 5 divided by that, find out how many seconds. So 5 kilometers divided by 0.0027 km per second is going to give me, clear, 5 divided by 0.0027. That's going to be, this is going to be times 1851.9 seconds. Now 3 kilometers per hour, so clear. 3 divided by 3,600 is going to give me 3 kilometers for every, 0.00083 kilometers per second. And once again, I'll divide 5 by that, so clear. 5 divided by 0.00083 is going to give me 6,024.1 seconds. And now we have to just figure out how many, which one. Okay, that's times 290. And that's going to give me 1.7 times 10 to the 1, 2, 3, 4, 5, 6 joules. And this guy, 700 times 1851.9 is going to give me, wait, there's something wrong there. Can't be that. 700 times 1851.9 is going to give me 1.2 times 10 to the 1, 2, 3, 4, 5, 6 joules. So you burn more calories or use more energy when you walk that distance at a leisurely 3 kilometers per hour. All right, chapter 6, problem 662 says, a bulky cow is leaving the barn as you try harder and harder to push her back. In coordinates with the origin at the barn door, the cow walks from x equals 0 to x equals 6.9 meters. As you apply a force with an x component, so let's see, where am I? Oh, gotta plug in this board. Second. All right. So let's see. So the cow is going from x equals 0 to x equals 6.9 meters. And as you apply force of F of x equals 20 newtons, 20.0 newtons plus 3.0 newtons per meter times x. 3.0 newtons per meter times x. How much work does the force you apply do on the cow during this displacement? All right, it's the area under the curve or the integral again. So let's go ahead and do that. Work equals from 0 to 6.9 meters, 20 newtons, and then that's plus or minus, plus let's see, here plus 3.0 newtons per meter times x, and that's dx. Okay, so that's going to give us 20 newtons x plus 3 over 2, right? 3.0 newtons per meter over 2, x squared evaluated from 0 to 6.9, 0 to 6.9 meters. And the answer is going to be 209 joules. And the work is negative because the cow continues to move forward in the positive x direction as you vainly attempt to push her backwards. Okay, so it's negative 209 because you were trying to push her backwards. So this all should have been negative the whole time. All right, that concludes chapter 6.